Okay, so the net, meaning the sum of all the forces, and the video that we just watched showed that really well. And if the forces are equal and in opposite directions, we call them balanced. And again, this is a logical kind of common sense kind of situation. If all the forces are balanced by equal forces, but in opposite directions, like these vector arrows are showing, the object is going to maintain its current motion. Notice that I didn't say it has no motion. This is probably the other thing, besides normal force, this is the only thing that sometimes can get people confused. If an object is moving and the forces on it are balanced, it's going to stay moving and doing exactly what it is doing at that moment. Right? It's going to stay basically like on cruise control. But if an object is not moving and you have balanced forces on it, it's going to stay not moving. So it's going to just keep doing whatever it is it's doing. Whether it's at that speed or whether it's stationary, it's going to keep doing that. And most of the time people will sometimes think, okay, if it's balanced, then that means there's no motion. And that is incorrect. If there's already motion and it has balanced forces, it's going to stay in its current motion. So it's like a car on cruise control.
A lot of times you'll see the word constant, like constant speed, constant velocity, something like that.
Yeah, and we're going to do an activity, I think Monday, with free body diagrams. And so usually after that, it kind of clicks. Either changing or constant are going to be our key words that we'll look at. So if an object is not moving, it's going to remain not moving, which is easy to understand. But this is the one, if an object is moving, it will continue moving at the same speed and in the same direction. So this is like the cruise control. So they're not moving, remains not moving, or if it does move, it's going to stay moving the way it is. And those are balanced forces. We know what balanced means. It means equal, right? So it's easy to picture these and imagine this. Kind of going along with this is something called inertia. And this was mentioned in the Bill Nye. It showed some examples. But this is the tendency of an object to resist any change in motion. This year we're just going to look at one of Sir Isaac Newton's laws of motion, and it's this one. Next year we're going to look at all three laws. So again, this entire unit is going to be kind of the base, the foundation for one of our units of force and motion next year. So again, the better you get it this year, the easier it's going to be next year. So this is the tendency of an object to resist any change in its motion. So if an object is at rest, it's going to stay at rest. And that's easy, because we know like things just like sit where they are unless something makes them move. Pretty easy, like those boxes on the Bill Nye. Those movers were like, come on boxes, come on. It's like, well, obviously the boxes aren't going to move. That's stupid, right? You have to move them, or something has to move them. But have we ever really thought like an object is going to stay in motion? It's like, no, everything wants to come to a stop. But what's really stopping things? If a ball's rolling across the floor and it's just rolling, and it doesn't hit a wall, why is it eventually going to come to a stop? What do you think, Andrew? Well, gravity's going to be working on it for sure, right? Gravity is part of it, right? What else is at work to slow that ball down? There's going to be friction, right? And so if you have friction, which in our world, there's friction almost everywhere. So that's why incorrectly we think, okay, every time something's moving, it's going to slow down on its own. Well, it's not really slowing down on its own. It's slowing down because friction is at work.
So I got a question. What if somebody decided to throw a ball on the moon, for example?
Going to keep on going.
Would it like
Kind of
leave the
cool.
atmosphere?
It could, right? It could. So if it's high enough and it's not going to be pulled by the moon's real weak gravity, it's just going to go and kind of keep floating, right? It's not going to experience friction. And that's going to be one of the examples of a location where there is almost no friction is in space. So if you can get it far enough away from the moon's pull of gravity, it's going to just continue on.
So what if you threw a baseball like as hard as you could, would it keep accelerating?
It should continue its same speed. It's not gonna gain, like once it reaches, I'm assuming it should just maintain its constant velocity. Once it reaches that speed, it's gonna just stay there. There's not gonna be anything that would interfere with it. And that's hard to picture, right? Because like if you throw a ball, you throw a baseball here, as far as you can, like you're launching it from the outfield trying to get somebody out at home, right? Eventually that ball is going to start to get pulled, like Andrew said, gravity's working on it, and the friction of the air molecules are going to start slowing it down, right? So at some point it's going to reach its peak velocity or speed, and then eventually it's going to start slowing down. Like that happens fairly quickly, right? But in space, it's not going to experience that friction or that gravity, so it's just going to continue to move, following the path that your hand threw it. Good question. Can anybody else, can you ever think of another situation where it's hard to stop? Oh, Paul, you have something to say or question? Question? What is it?
What would happen if you just threw something at the Earth on the moon?
If you're on the moon and you threw something at Earth,
Yeah, like where would it end up?
well, it probably wouldn't make it to Earth's atmosphere, right? Because it's so far away. You would leave the moon's atmosphere and gravitational pull, and then that object would just end up in space, right? It would never make it into Earth's atmosphere where we would experience it. Does that make sense? Because it's so far away. It's not like you're just like across the hall, like I can throw something into Mr. Trainer's room, right? We're too far away. Where, you know, if you're going from the moon to the Earth, it would just end up in between the two in space somewhere. I'm assuming. That'd be my guess. I've never tried it. It's a good thought. Anywhere else, think of a situation now that winter's coming on. Anybody think of any situation where it's hard to stop? Ice, right? So most of the time there's friction all around us. And so things come to a stop. And that's why this part of inertia sometimes is a little bit more tricky, because you're like, yeah, things always want to stop. Why would they stay in motion? Well, the only reason they're coming to a stop and not staying in motion is because of friction. So in space or on ice, if those places have very little friction, then the motion is easier to see. It just continues without an additional push or pull. Okay. So really inertia is, it's just going to keep doing whatever it's doing. So if it's at rest, it stays at rest. If it's moving, it's going to stay moving. So if that's how you can think of it, that kind of helps. So if you watch this, the van hits the car and comes to a stop. Why doesn't the ladder come to a stop? Like why does it keep moving? The van or the truck, whatever it is, it stopped. Why didn't the ladder stop with it? What do you think, Isaiah?
It wasn't attached to anything?
Yeah, like it wasn't strapped down. So what would happen if somebody was in a vehicle and the truck came to a stop? If you come to an abrupt stop and you're not tied down in the car like the ladder was, what would happen? You'd fly out, right? Which is why there are seatbelt laws. Okay, so just because the ladder is on the truck, if it's not secured to the truck, then it's not going to respond. It didn't get the stopping force that this car provided. The van did, but the ladder didn't. So that ladder is going to stay in motion. Now, why did it eventually fall? Why didn't it just keep on going straight? What other force acted on it? Gravity, right? The normal force that the van was providing, that solid to solid, is gone. So the force acting on it now is gravity, which is why it pulls it down. Oops. I hate when that happens. Okay. And another thing with inertia is the more mass an object has, the more inertia it has. And it makes sense because it takes more force to make a change. It takes more force to get a heavy object moving, and it takes more force to stop a heavy object that is already moving. So if I give you a choice, I will give you $1 million if you can push a sports car that's not running 1 meter across the parking lot, or you can choose to push a semi 1 meter. Which vehicle are you going to choose to try to push to hopefully get my $1 million? What would be the best chance that you could maybe get that $1 million? Paul?
Sports car,
Why?
because it has less mass.
Possibly you could get it to move. Maybe, right? Even if you put it in neutral, both vehicles, maybe you'd actually get the sports car, right? Would you have any chance at all with the semi? Probably not, unless you're Ronan the Incredible, right?
Nah, I can just grow up with my dad. He's a truck driver, so.
Oh, so you have special powers. You can get a semi moving with just a push. With you just pushing, yeah. Boards. All right. So, and it's pretty easy, right? Let's imagine somebody in a sports car is traveling 55 miles an hour down the road and a deer jumps out. Or imagine a semi driver is traveling 55 miles down the road and a deer jumps out. Who has the better chance of putting on the brakes and not hitting that deer?
Sports car.
Sports car, right? Less mass to try to get stopped. So it's harder to get bigger masses moving and harder to stop them. Okay. This is also known as Newton's first law of motion. We'll watch a couple videos and demonstrations of this at the end. Okay. And I'm gonna put some extra links into Google Classroom where we're gonna get to practice some of this stuff. I don't have them in yet, but there'll be a whole post with a bunch of different games that will take you to different sites, and we'll look at some of those later on too. So we can't talk about motion without this big idea known as friction, which we've already mentioned. But it's the force that occurs when two objects are in contact. And so this whole unit's about contact. So everything we're talking about is experiencing friction. As things touch, there's friction. And I know a few of you did this the other day when you were just even looking at your vocab and you saw the word friction. You're like, oh, friction, right? That's the kind of the go-to image or thought. If you put your hand out the window or wave it like this, what do you feel? Don't hit Max. You feel those air molecules, right? And so we don't see them. We can see the effect of wind and air, but we don't really see it, so it's easy to kind of ignore. But you can feel it. If you've ever stuck your hand out the window of a car and you're like this, you can kind of feel like you're cutting through the air. And as you put your hand like this, that wind, that air slaps it, right? It is a strong force. And so we need a more powerful force to overcome that if you want to have motion that is moving against that. It's always going to be opposite the direction of our motion. So if our applied force is to the right, then friction is going to be working to the left. And whether that's between the surfaces that are touching or whether like the air resistance that is involved, let's face it, it's a good thing there's air all around us or else we wouldn't be able to live. And so as we have things that are moving, we try to account for that. We try to balance working against that air to get things that we want to move more easily. And we'll talk about a lot of these. So there's lots of different specific types of friction. One that we've already mentioned is drag. And this is a special type of friction that opposes the motion of an object that is moving through a fluid or a gas. Or excuse me, a gas or a liquid. They call it just a fluid. So a boat, right? It has to cut through the water. Those water molecules are kind of holding, like slowing its progress down, just like air for us on land, right? So anytime something is going through a gas or a liquid, it's a special type of friction called drag. And again, we see weight, which is gravity pulling down, we see lift, and this is not normal force because it's not a solid to a solid, so this ball is experiencing lift, the push of air molecules from the bottom. And typically, friction and drag are going to affect the motion of all objects. They may even cause the object to slow down and stop unless another force ends up being exerted. So if I, obviously if I hold on to this book and I keep pushing and pulling it, it's gonna keep moving as long as I apply the force. If I just push it, it comes to a stop pretty quickly, right? So I'm not applying a big force, so it comes to a stop pretty quickly, right? Same thing with, all types of things that are in motion. If you don't continually apply that force, then it's going to fairly quickly come to a stop. And the more friction there is, the quicker it will stop. The less friction, the more it keeps going. Okay, so a ball rolling on grass is eventually going to stop because of the friction. Give me another example of something slowing down because of friction. Not because you quit applying the force, but like if you apply the force and just let it go. Give me something that you can think of in your everyday life. Okay. So Max dropped his pencil. But what really stopped it when it touched the table? The table. So then the normal force pushed back up on it, right? Okay, so what's that paper experiencing? It's experiencing lift, and that's a form of drag. Specifically, it's a form of air resistance, which is a type of friction, right? What about if we, hold on, let me see something real quick. I'll wait for that. So what do you think? Something that is moving that's going to come to a stop. So you have a spot to jot something down, right? Isn't there? Yes? Yeah. So just one thing. Somebody want to share what they're writing?
With like a water bottle like rolling on the ground, would that work?
Yeah. If there was no friction, that bottle would just keep rolling forever.
Yeah.
Sure.
Isaac, what's something with your dirt bike or whatever you want? Just think of in general, like what if you're accelerating and you let off, what's gonna happen?
It'll stop.
Right away, eventually.
If you don't put the brakes on, will it coast to a stop?
Yeah,
What's slowing it down?
friction.
The friction, right? So any kind of tires or wheels, if you quit applying the force, even if you don't hit the brakes, it's eventually just gonna peter out, right? It's gonna roll, 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 and eventually stop. All right, so you get something jotted down? Or you crash into something. That's more likely with Isaac.
Yeah.
Poor Isaac. Okay. So we kind of already spoiled this, but that's okay. We said that there are two situations that we've talked about already. What are two situations where there is very small friction or almost no friction? In space, right? In outer space, for sure. And so an object is just going to keep on doing whatever it's doing, whether that's rolling, whether that's floating, nothing's going to stop it, right? What was the other one we said as winter's coming on? Yeah, ice. Right, there's actually one more, and there's an air hockey table. Has anybody ever played air hockey? Okay, so you turn the table on and there's like this small little barrier of air and that the puck sits on, right? So it's providing a little bit of lift, so it reduces the contact from the puck to the actual solid table. And so it's kind of hovering, right? So in a way, it's causing a very, very, very small amount of friction, but it reduces the majority of the friction, right? Because there's no contact. It's just hovering and levitating in a way as it glides across the table. And we'll look at kind of a little video, but there's those tiny little air holes along the whole table, so it just causes the puck. And so you don't have that contact, that touch, right? There is a little air resistance as it flies back and forth, but it's not experiencing the contact like my book, right? It allows that puck to slide more freely to kind of simulate ice a little bit better. There's something else called dry ice. It forms a barrier as well. So kind of like the air is forming a barrier on an air hockey table, the carbon dioxide gas, it goes straight from a solid to a gas. It skips the melting phase. And we call, this is a special type of phase change. And so it forms a barrier. So it's used a lot of times like in haunted houses and in theaters, like if you're trying to have smoke or fog. But at room temperature, it will go from a solid straight to the gas, right? And so if you have a solid block of carbon dioxide, you put it on the table and we'll watch a video and like it like scoots all around. It looks like a big ice cube almost. Because that barrier, that ice kind of the gas gets underneath it and it allows it to like slide and slip around. And then obviously ice in an object in space. So obviously an air hockey table is very specific. Dry ice is very specific, but ice can happen, it's probably our most common for sure. And then obviously we don't get to experience outer space, but it's friction free there as well. And so what do all of these have in common? What do they help us avoid, or what don't they have? Friction, right? Very, very minimal friction. And so if you're trying to make something be able to keep moving, you want to reduce the friction. If you're trying to increase friction, then it's because you're trying to get something to stop. So like if I'm on ice, I probably want to stop. I want to have something that's going to give me some traction. So we'll talk more about good of friction and bad of friction tomorrow.